Hi guys, James Electronics Tutorials here, back with another video, and today this video will kind of be an introductory video for Applied Electromagnetics, AEM. And so to start that topic off, we will be starting by looking at traveling waves, as this is quite fundamental to Applied Electromagnetics. So yeah, let's have a closer look at that. Okay, so to understand the parameters of a traveling wave, let's consider a one-dimensional traveling wave for an example. So here we have y of x and t equal to a times sine or cosine, let's go with cosine, omega t, plus minus, let's go with minus, beta x, plus minus, let's go with plus phi naught. This is the initial phase shift, and beta is the phase constant of your traveling wave. So why I try to make that clear that it can be plus or minus, because that influences the direction of your traveling wave. So here we have minus beta x. So because there's a minus sign there, that means our wave is traveling forward along x. And the opposite here, if it was a plus, that means our wave would be traveling backwards along x. That's the kind of convention here. If I draw this, plus goes this way, minus goes this way. You can kind of see it here, because this way is forwards, this way is backwards. For F there for forwards, B there for backwards. This should hopefully click. So let's move on. A means amplitude. This is the amplitude of your traveling wave. Here we have omega, that's the angular frequency, known as 2 pi f radians per second. Or 2 pi over t radians per second. Because 1 over f equals t. And here we have the phase constant, beta, and that is equal to 2 pi divided by lambda radians per meter. And lambda, the wavelength of the traveling wave, is equal to c over f. F is frequency and c is the speed of light. You can approximate that to 3 times 10 to the 8 meters per second. And frequency is hertz, or alternatively per second. Let me try and draw this out. So the units for speed of light is meters per second. The unit for frequency, is hertz, or inverse second. So inverse second and inverse second here cancel out, and you're left with meters for your wavelength. And here we have phi naught equal to omega L over c, and the unit here is radians, just radians. And the last thing here is phase velocity. Phase velocity is not something that's part of this equation, but it's a parameter nonetheless, and you could use the equation here for the one-dimensional traveling wave to calculate your phase velocity. So here it is. Phase velocity is equal to omega over beta. That's your angular frequency divided by your phase constant. And let's see if the units check out here. Radians per second, radians per meter. So the radians will cancel out. Inverse m, 1 over m, in other words, is equal to m. And so what we're left with here, running out of space, the unit here simplifies to meters per second, and that checks out. So these are all the main components of a traveling wave that you should know. Okay, there's one other thing you need to consider with your traveling wave, and that's if your wave travels through a lossy medium. So when your wave travels through a lossy medium, the wave amplitude will decrease exponentially the further the wave travels into the lossy medium. So we can put this in terms of an equation. It's just the same as before, just one extra thing. Y of x and t is equal to a, and here it is. It's just e to the minus alpha z. Not alpha z, alpha x in this case. And same as before, cosine omega t minus beta x plus phi naught. The only thing that's changed here is that exponential term there. And what alpha is the attenuation constant. And the unit for this is nepers per meter, or NP. Just to save some time there with the handwriting. And yeah, that's just the main change. And if you look in the top right of the screen here, I've used MATLAB to kind of simulate this because it's not so easy to draw for me. Okay, so I've essentially simplified, very simplified actually, the equation. So that's just a single variable, so it's easier for me to plot in MATLAB. It's less complicated. And if you notice, underneath the fourth line, after I've wrote hold on, I've plotted what's called the wave envelope. It's those dashed lines that go from the top and the bottom of the wave and kind of close in, but don't cross that wave. So it's just the attenuation term multiplied by the amplitude, and that's it. And of course, for the wave envelope on the bottom, it's minus amplitude to get the bottom half. And this is all for attenuation, I think. So now I think we're ready to tackle some problems about traveling waves. Alright, here's question 1. This is the one-dimensional traveling wave of an electric field, and its unit is in volts per meter. I have 3 questions here. What is the direction of the wave travel? What's the phase velocity? And what's the amplitude after 200 meters? Take your time if you need to and pause the video to work on the solutions for these questions. Okay, so for question 1, A, what's the direction of the wave travel? The sign is a plus, so therefore this wave travels backwards along x. Okay, and question 1b, what's the phase velocity? This is omega divided by beta. Here we have omega, and this is beta here. So it's just a case of 6 times 10 to the 12 divided by 2 times 10 to the 4. This is equal to 3 times 10 to the 8 meters per second, which is also the speed of light. Now question 1c, what's the wave amplitude after 200 meters of wave travel? So we just do a bit of plug and play here. We have 50 times e to the power of minus 0.05. 0.05 is the attenuation constant, isn't it? Just write that there. Times 200. This is equal to about 2.27, oops, 2.27 millivolts per meter. This is the answers for all the questions here in question 1. Okay, here's question 2. This is a one-dimensional traveling wave once again, and this time it's not the electric field, it's a voltage. And in question 2a, I want you to find 3 parameters. I want you to find the frequency, the wavelength, and the phase velocity. And in question 2b, when Z is equal to 2 meters, the amplitude is equal to 3.68 volts. What I want you to do is to calculate the attenuation constant alpha. Pause the video if you need to and work on the solutions. Okay, let's start with question 2a and find the frequency. Frequency we get from the angular frequency, and that's the case of omega is equal to 2 pi f. Dividing by two sides, we rearrange for frequency, like so. So in this case, it's 4 times 10 to the 8. Oops, not 4 times 10. 4 pi times 10 to the 8. Divided by 2 pi will give us 200 megahertz. That's our frequency. And now we want to calculate the wavelength, lambda. So in this case, we use the formula 2 pi divided by beta, the phase constant. So here we have 2 pi divided by 10 pi. The pi will cancel out. 2 over 10 is the same as 1 over 5, and 1 over 5 is 0.2 meters. That's that, and now let's find the phase velocity. Draw that a bit neater. There we go. So this is omega over beta, 4 pi times 10 to the 8 divided by 10 pi will give us 40 times 10 to the 6 meters per second. There we go. That's question 2a solved. Now let's move on to question 2b. So when Z is equal to 2 meters, the amplitude is equal to 3.68 volts. So our goal here is to find the attenuation constant alpha. So let's write this down. 10 to the e minus alpha times 2, because Z is 2, is equal to 3.68. So we start by dividing both sides by 10. So we got 0.368 here. Then we take the natural log of both sides. Will give us minus alpha times 2 is equal to ln 0.368. Okay, and we'll start the second row here. What we want to do next is divide both sides by 2. So we have minus alpha is equal to ln 0.368 divided by 2. And one more step here is to multiply both sides by minus 1. So then we get alpha is equal to minus 1 times ln of 0.368 divided by 2. And if you want to be posh, you can use this little rule here. I'll write it next to the question. A times ln b is equal to ln b to the power of a. So if you apply that rule here, what we get is the inverse of 0.368. Let's write that here. 1 over 0.368 divided by 2 will give us our answer. And that will be an answer of approximately 0.499 nepes per meter. And that is question 2 all solved. So yeah, that's all I have for today's video on travelling waves. I hope you enjoyed and learned something new in terms of that and applied electromagnetics. And yeah, to support the channel, I really appreciate it if you do. Is just to subscribe, leave a like, leave a comment if you have any further questions about electrical engineering, or if you'd like me to cover any further topics related to electrical engineering, please let me know. And yeah, that's it. Have a good day.